today we're going to talk about vectors in a two-dimensional plane. So first of all, whenever we say vectors, we're talking about a quantity that has both magnitude and direction, right? So vectors always have magnitude and direction. For example, like the force here, this man applies to the box, it has a magnitude, right? How strong the force is. It also have a direction, right? The force the man applies is going up to the right corner, right? So that's the force is a vector. If you have taken some physics class, you may have know about the vectors already as well. So for the first example, let's look at which of the following is better described by a vector or a scalar. The cost of a Super Bowl ticket, is it a vector or a scalar? Well, the key is to look at if it has direction or not, right? Both vectors and scalars, they have magnitude, but only vector have direction. And the cost of a Super Bowl ticket obviously does not have a direction, so that's a scalar. The wind at a particular point outside, well, the wind have both direction and magnitude, right? So that's a vector. The number of students at UW Stout, again, the number of students have no direction, so that's a scalar. And the velocity of a car, so the velocity actually have direction as well, right? It could go north, it could go south or east or west, right? So this is a vector. And the speed of a car, when we talk about the speed of a car, this is just a number, right? So that's a scalar, like a 50 miles per hour, 60 miles per hour, that's just a scalar. Okay, so that's the basics. Now let's look at more on how to graphically represent the vector. So in my xy plane here, I have 2 points A and B. Between A and B, I can use an arrow here to connect them, and this is exactly a vector that has direction and the magnitude. And my A point, that's where the vector starts, is called the initial point. B point is where the vector ends, that's called the terminal point. And we write our vector as AB with the arrow on top, right? That means our vector starts at A and ends at B. And sometimes we also use this lowercase letter with an arrow on top to indicate a vector. Now let's look at how do we find the value for this vector. My point A is 2, 3, right, from my graph. My point B is 6, 5 from my graph. So to find my vector A to B, the component form, we'll learn a different form later, right? So keep in mind this is called the component form. It's where we use this point bracket in with numbers in between, right? It kind of looks like a point notation, the ordered pair, but instead of using parentheses, we're using this pointed bracket now to indicate that's a vector. And for the numbers inside, all we need to do is to subtract the corresponding component, the corresponding coordinate together to get that component. So 6 minus 2, that's my first component, is 4. 5 minus 3, that's my second component, is 2. So I say my vector AB is 4, 2. Okay, so we use a pointed bracket to include a order pair number inside. That's called a component form. Now, if you look at this vector OP, what is this vector value? So my O now is 0, 0. Right? My P from the graph is 4, 2. And again, we're going to subtract the corresponding coordinate to find my vector from O to P. So 4 minus 0 is 4, 2 minus 0 is 2. You can see my OP vector is 4, 2 as well. This actually tells me that my two vectors are the same. They're both 4, 2, right? So that's where we can talk about equivalent vectors. We could have a bunch of vectors starting and end at all different locations, but as long as these vectors have the same magnitude and the same direction, then they are basically the same vectors. So we call them equivalent vectors, right? For vectors, because it has magnitude and direction, so both magnitude and direction has to be the same. Right? If you look at the graph, all these four vectors are really equivalent. They're really the same vectors. If you just move one to another, they would coincide. Right? So all of these are really the same vectors. For a vector, it doesn't matter where it starts and where it ends. It only matters what's its magnitude and what's its direction. And similarly, we can talk about the parallel vectors. So these vectors now, these four on our graph, they are not the same vectors. They're not equivalent, right? Because they may have different directions. They are actually opposite directions to each other. Right, like the red and the blue, they're opposite. This dark red one and the green one, they are opposite as well. And they have different magnitude, right? The red one and the blue one again have different magnitude. The green one and the red one have different magnitude. So these are not equivalent vectors, but if you think about the line they are in, all these vectors are lying in parallel lines, right? So these are called the parallel vectors, and the parallel vectors may have different magnitude, or they could have the same magnitude, right? Like this blue one and the green one, and they may have the same direction, like the red, these two red ones. Actually, the green one and the red one, they have the same direction, but they could have opposite directions as well, right? So parallel vectors, they could look like this, opposite direction, or they could look like this, the same direction, and the magnitude could be different or the same. Right? Now, how do we find the magnitude of a vector? So this actually comes from the Pythagorean theorem. If we have a vector that's denoted as components A, B, which means my x component is A, my y component is b, and this is a right triangle, right? So if you use the Pythagorean theorem, you will see the magnitude would be square root of a square plus b square. Okay, so this is an important formula that you want to know. Now let's look at this example 2. For 3 points A, B, C, which of the vector is longer? Is AB longer or is AC longer? So to find this problem, we have to find out the vector lengths AB and AC, right? We need to find out their magnitude first, then compare them. So I'll give you some time to find your answer, and then you can pause the video, find your answer, and then come back to check the answer with mine. So here is my answer for this problem. I found my vector AB and AC first using the terminal point minus the initial point. And once I have the component form, I can use my formula here, right? Square root of a squared plus b squared to find the magnitude of each one of them. So we can see that the magnitude of AB is 5 and the magnitude of AC is 29. So obviously the magnitude of AC is bigger, so AC vector is longer for this problem. Okay? Now, for vectors, we can actually multiply a vector with a number and also add or subtract our vectors. So here, if we have a number m, we're multiplying it with a vector. All we need to do is to multiply the number into each component, right? It's pretty simple. For adding and subtracting vectors, it's the same thing. If we're adding two vectors, we can add the corresponding components together. And if we're subtracting vectors, we can just subtract the corresponding component together, right? So that's how we find the algebra answer for the vector. However, the graphical illustration is actually more important for us. This graph tells us if we have two vectors u and v, then u plus v actually is this diagonal made by the parallelogram of the vector u and v. Okay, so this graph may be a little bit complicated for you, but you just want to think about two vectors here, u and v. If they start at the same initial point, then u plus v is going to be this diagonal, starting at the same initial point. Okay, that's our parallelogram law. And another way to add vectors, we can actually combine tail and the tip together. So if this is my vector u, and now I move the initial point of my vector v to the terminal point of my vector u. If I draw my graph in this way, then the tip of my vector u to the tail of my vector v, this is my answer for u plus v graphically. And you can see these two graphs are actually talking about the same vector, u plus v. They are equivalent. Right? So similarly, when we want to look at u minus v now, look at this picture again. My u is here, my v is here. In order to find my u minus v, I need to find my negative v first, because u minus v is really u plus a negative v. Right? And the negative v means the same magnitude as my vector v, but pointing in the opposite direction. Right? Negative sign makes the direction to be opposite. So now I'm using these two vectors, and if I form the parallelogram and look at the diagonal, this is going to be my u plus negative v. That's my u minus v. Right? And the same thing here, if I shift my blue vector here to the two vectors I had earlier, then you can see this vector exactly connects the two terminal points of my vector u and v. Right? So my u minus v is actually the other diagonal in this parallelogram. Right? So this parallelogram law is really important. It tells us the two diagonals in my parallelogram formed by vectors u and v are going to be u plus v and u minus v. Okay? Now, some other properties we can have when we do algebra on vectors, we could swap the orders of the two vectors when we add. Right? It doesn't matter. We could change where the parentheses is at. We could group the vectors in different ways when we add them. It doesn't matter. And we can distribute the number into the vector, right? So all of these normal things that we could do with our numbers, we can still do them with our vectors when we add or subtract the vectors. Right? That's really nice. Another important topic we need to know is the unit vector. So unit vector is a vector that has length 1. Right? Length means magnitude. So a unit vector also always have magnitude 1. And if we have a vector v here, and we want to find its unit vector, meaning we need to make its magnitude to be 1, what do we do? Well, if we know this vector v has a magnitude 2, then all we need to do is divide it by 2. Then its magnitude would become 1. Right? If we know its magnitude is 3, then all we need to do is to divide it into 3. Then we have a magnitude 1 vector. Right? So this is the formula here that we use to find magnitude of a vector. We use, to find the unit vector of a vector in the same direction. All we need to do is to use the vector itself, divide it with the magnitude, like what we did here in the picture. Then we get to the vector with magnitude 1, but still in the same direction. So that's the unit vector we want to find. Right, so for this example 4, let's find the unit vector in the direction of this vector v, negative 2, 5. So this is really simple, right? All we need to do using our formula is to find the magnitude, then divide it into the original vector v, right? You can pause the video and work on this by yourself, and then come back and check your answer with mine. Here is the answer for example 4, right? All I need to do is to find the magnitude, square root of 29 that we did earlier. Then we divide the vector v with that square root of 29, right? And remember the algebra we talked about earlier. If we divide a number, just like multiplying a number, we multiply it into each component. When we divide, we also divide it into each component, right? So that's my final answer for the unit vector of negative 2, 5. Right? Make sure you write your answer in the component form as the problem asks. Now let's look at this one. This is a little bit different. We want to find a vector in the opposite direction of vector v, that's 1, negative 3, and has magnitude 4. I'll give you some time to think about this problem, work on that, then I'll talk about how to do this. So for this problem, one thing that's different to the unit vector is that we need the magnitude to be 4 instead of magnitude to be 1 now, right? How do we make a vector to have magnitude 4? Well, it's really simple. We just multiply 4 to that unit vector, right? Because this unit vector always have magnitude 1 by definition. Now, if we multiply 4 on something with magnitude 1, it's going to have magnitude 4 now, right? That's how we take care of this 4 part. Now, how do we make it opposite direction? Well, we just talked about it. If we multiply a negative 1, then the vector is going to turn to the opposite direction, right? So that's how we find our answer. And our unit vector, again, is v over the magnitude of v, right? That's what we want to compute to find the opposite vector with magnitude 4. So my magnitude of vector v, again, 1 squared plus negative 3 squared would be 1 plus 9, that's 10. Right, so I'm going to do negative 4 times this 1, negative 3 vector divided into negative 10. Right, so what's your steps here? We divide each component by square root of 10, and then we multiply -4. So the first component become negative, and the second component become positive. And that's my final answer for this problem. Now the last thing we're going to talk about is this standard basis vector. So instead of writing this component form vectors, sometimes, especially in physics, you would have seen this I, J, and sometimes K notation. This is called the standard basis form, and this comes from the coordinate plane, where our I vector is this unit vector in the x-axis direction, 1, 0. Our j vector is the unit vector in the y-axis direction, 0, 1. So now if you think about any vector, AB here, this AB vector has to come from some x component plus some y component because of the parallelogram law, right? And this x component depends on a, and a would be a times 1, right? So we're doing a times I component to get to the x component part, and then we add with this y component part, which comes from my b here, and the b times 1 is still b, right? So my b times j gives me this y component, and then we add them together. Right, so this component form AB is the same as AI plus BJ. Okay, so this part on the right is called the standard basis form, and on the left it's called the component form, and they are just different notations for the same vector. Right, and every vector can be expressed by a I'm sorry, let me remove this so you can see it better. Every vector in the plane can be expressed by a combination of scalar multiples of I and j because of that parallelogram law I just showed you, right? And just be careful when you write these kind of expressions. Do not write your expression like this, AI, BJ, with pointed bracket. This is wrong, right? If you use pointed bracket, we only have numbers A, B. There's no I and J anymore. If you use I and J, then there's no pointed bracket and comma anymore, right? You can only choose one of these notation, but do not combine them together. That is wrong. Okay. Now the last example I want to show you today. Let U be a unit vector that forms an angle of 225 degrees with the positive x-axis. Express U in using standard basis vectors. So my positive x directions is right here, 225 degrees, which would be 180 plus 45. Right, so this is my U vector. Okay, and we want to express this U vector using the standard basis vectors. And that means when we think about this U vector, we need to think about the x component and the y component. That gives us the ij term we need. Right, so the x component for our U vector would be right here, and it has to be a square, right, because of the parallelogram law. So this is my x component that goes with I, and my j component is down here, right? That means my j component that goes with y and j, we need to think about how many I here we have and how many j down here we have to write our answer. And the key here is u is a unit vector, right? So the magnitude of this vector u is 1. This hypotenuse now in my triangle is 1. And my angle here is 225 degree. 225 minus a 180 would be 45 degree, right? So if you just look at this triangle here, this right triangle here, I have my hypotenuse is 1, my angle is 45 degree. Then I should be able to find these two sides easily, right? My x would be 1 times cosine 45 degree, and cosine 45 degrees is square root of 2 over 2. Right, my y again would be 1 times the sine 45 degree, because that's the opposite side, and the sine 45 degree again is square root of 2 over 2. Right, so that's my answer in the right triangle. But if you look at this picture in the xy plane, my u is in the third quadrant, and that means x and y are both negative here. Right, because it's in the third quadrant. So my component form of my vector would be xy components are both negative square root of 2 over 2. Therefore, my standard basis form, that's what we want in this problem, using the I and the j notation, would be negative square root of 2 over 2i plus a negative square root of 2 over 2j. Right, because it's a plus, so plus a negative number, so I'm just going to write it as minus square root of 2 over 2j now. Right, these two vectors, they are equivalent.